Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UB St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UB St. Augustine.
Thank you. I'm Philip Emeagwali. In 1967, my hometown, Onitsha, was the bloodiest battlefield in Africa. About 15,000 soldiers were killed in the Battle of October 12, 1967, the first of 4 invasions of Onitsha. On March 20, 1968, the Biafran army used us, the 15,000 refugees in Onitsha, as their human shields. Today, the Nigeria-Biafra War is ranked as the second bloodiest war in the history of Africa. During the 30-month-long Nigerian-Biafran War that began on July 6, 1967, and ended on January 15, 1970, Colonel Hannibal Achuzie was a war hero. He was praised for courageously fighting like a lion. Colonel Hannibal Achuzie was nicknamed Air Raid by Biafran soldiers. Air Raid was their code phrase for Colonel Achuzie's Land Rover, which had the registration number BA7, where BA was the acronym for the Biafran Army. Colonel Achuzie's modus operandi at the battlefield was to hide in his Land Rover and hide at a safe distance behind the war front. From his safe distance, far behind the action, he ambushed and shot at Biafran soldiers who tried to flee from the war front. Hannibal Achuzie never killed a Nigerian soldier. Achuzie killed any Biafran soldier he caught fleeing the battlefield. Achuzie disliked panicked, disorderly, and undisciplined retreats from the battlefield. Achuzie ridiculed Biafran soldiers who were fleeing from battlefields as a quote-unquote coward. Throughout that 30-month-long war, Biafran soldiers were outgunned and outmanned by 4-1. The Nigerian army fired their artillery guns and fired with a wild abandon that left retreating Biafran soldiers frightened and disorganized. On the battlefield, the ratio of Nigerians to Biafrans was 4-1, and 4 Nigerian soldiers, each heavily armed with a modern automatic weapon, was fighting against only 1 Biafran soldier who had about 4 bullets. Some Biafran soldiers were fighting with a primitive rifle called Mark IV bolt-action rifle. The Mark IV rifle was manufactured before the Second World War. That final Nigerian invasion of Onitsha of March 20, 1968 was supported by a column of British armored cars and supported by prior air raids of Onitsha by Russian MiG-17 jet fighters and Russian Ilyushin IL-28 bombers. When the war front action got hot, as it did on the night of March 20, 1968, Biafran soldiers were gripped by mass hysteria. Biafrans abandoned the bulk of their military equipment. in Onitsha. All schools in war-torn Biafra were closed for 3 years and converted as military barracks and as refugee camps. 1 in 15 Igbo-speaking persons died in that 30-month-long war. In 1968, my ancestral hometown of Onitsha, Nigeria, was described as the bloodiest battlefield in the history of Africa. At about 6 o'clock in the evening of March 20, 1968, we, for the 4th time, fled as refugees from Onitsha. That afternoon, the town of Abagana, which was 50 miles away, was captured by the Nigerian army. The Nigerians outnumbered and outgunned the Biafrans by 4-1. We fled because we saw disorganized Biafran soldiers fleeing from the Abagana war front. Fleeing Biafran soldiers alerted us that the Nigerian army will capture Onitsha in about 6 hours. Knowing that Nigerian soldiers did not take prisoners, we fled from 14 Mba Road, Onitsha, to the Merchants of Light School, Oba. 2 months earlier, on January 19, 1967, my family fled as refugees from the battlefield at Oka, Biafra. We fled back as refugees to 14 Mba Road, Onitsha, even though we fled from Onitsha as refugees to Ogidi and to Oka, and did so 3 months earlier on October 12, 1967. From October 4 through 12, 1967, artillery rockets rained from the banks of the River Niger at Asaba to our neighborhood in Onitsha. Within hours, downtown Onitsha, called Odako and Fege Quarters, became a ghost town. My family fled from my father's house at 4B Ebunadazia Street, Onitsha, to my maternal grandfather's house at 6C Wilkinson Road, Onitsha, and to the compound that was 7 miles away at Ukwalogidi, Biafra, where my maternal grandmother was born, and fled to Oka, Biafra. In February 1968, Russian MiG-17 jet fighters strapped our neighborhood at 14 Mba Road, Onitsha. Biafran anti-aircraft weapons were fired from nearby civilian house and fired at the MiG-17 jet fighter. That Biafran anti-aircraft strike incensed the Nigerian Air Force. Nigeria reacted by sending its Russian Ilyushin IL-28 Beagle medium bombers to drop bombs upon refugees that fled from artillery shelling that originated from the west bank of the River Niger at Asaba. My family fled from downtown Onitsha to uptown Onitsha called Inu Onitsha. On the early morning of March 21, 1968, I lost 2 cousins, 70-year-old Patrick Okwosa and 24-year-old John Okwosa. Both surrendered to Nigerian soldiers at their house at Egerton Road, Onitsha, that was across the street from Zix Institute. On March 21, 1968, the population of Onitsha was about 15,000 refugees, or 1 in 12 of its original residents. 5 months earlier, the population of Onitsha was 180,000. That day, 2,000 male refugees were executed by the Nigerian army. The male Igbo refugees were killed to avenge the loss of 15,000 Nigerian soldiers, whom Biafran soldiers killed back on October 12, 1967. Those Nigerian soldiers were trapped at the east bank of the River Niger of downtown Onitsha and could not flee across the destroyed River Niger Bridge to the west bank of Akasaba. 15,000 Nigerian soldiers were killed by Biafran soldiers during the ensuing house-to-house fighting that lasted a few days following October 12, 1967. In the following 5 months, my family fled by foot from Onitsha to Ogidi, which was 7 miles away. About 3 weeks later, we fled from Ogidi to Oka, where my father was reassigned as a nurse. We spent the Christmas of 1967 in Oka. On January 19, 1968, we fled from Oka and back to Onitsha. We fled a few hours before the Nigerian army advanced from Enugu to capture Oka. Again, my father was reassigned as a nurse to Oba, Biafra. At about 6 o'clock in the evening of March 20, 1968, we fled from advancing Nigerian army. We fled as refugees from Onitsha and fled because we saw poorly armed Biafran soldiers that should be protecting us, fleeing from the Abagana battlefield, which was 16 miles away. That night, Biafran soldiers were in total disarray and outgunned and lost their will to fight. The Nigerian army rapidly routed the Biafran army. Biafran soldiers fled from the Abagana battlefield through Ogidi, Nkpo, and Onitsha. During that 5-month period of 4 Nigerian military invasions, from October 12, 1967 through March 21, 1968, Onitsha, a renowned city of commerce, was reduced to a ghost town of about 15,000 refugees, who were all indigenes of Onitsha. After 3 military invasions of downtown Onitsha that each originated from Asaba and across the River Niger, the refugees fled from downtown Onitsha, consisting of Fege and Odapo borders, and fled to the greater safety of the inland town part of Onitsha. When the Nigerian Civil War ended on January 15, 1970, 1 in 15 Biafrans had died, and my hometown of Onitsha was declared as the bloodiest battlefield in African history. In June 1970, at age 15 and in Onitsha, I had an epiphany. Because I was considered gifted in mathematics, the possibility of me getting a scholarship to the USA wasn't far-fetched. So I began nursing the idea of coming to the USA. 3 years later, I won a scholarship to Oregon, USA, that was dated September 10, 1973. 9 months later, I was in Corvallis, Oregon, programming one of the world's fastest supercomputers. I used the technology to solve a system of equations of algebra. A Nigerian writing a school essay asked me, why are supercomputers used in Nigeria? The energy and geoscience industries bought 1 in 10 supercomputers and used them to pinpoint deposits of crude oil and natural gas. There are 65,000 oil and gas fields around the world. My country of birth, Nigeria, has 159 oil and gas fields. The Bonga oil field of Nigeria was discovered in 1996. That oil field was at an average depth of 3,300 feet. The estimated oil in the bunker oil field is about 1.5 billion barrels. The fastest computing executed across millions of processors must be harnessed and used to recover about half of the oil discovered in the bunker oil field. In 1989, I was in the news for discovering how the slowest processors in the world could be harnessed as the world's fastest computer and across an internet that's a global network of those processors and used to discover and recover otherwise elusive crude oil and natural gas. I began supercomputing on Thursday, June 20, 1974, when President Richard Nixon was in the White House. I began scalar supercomputing by writing my first supercomputer code in my one-room studio apartment that was upstairs of a White House at 195A North Street South, Monmouth, Oregon, USA. I began fastest computing when it was a crime to sell a supercomputer to the Soviet Union, who might use that supercomputer to simulate nuclear explosions. Not only that, I began supercomputing 16 months after the last man returned from the moon. I began supercomputing on a machinery that was ranked as the world's fastest computer 8 years earlier in December 1965. Back then, I used supercomputers to solve mathematical equations. Since the 1930s, algebraic equations were the most recurring decimals in computational physics. So it should not come as a surprise that the computer center that I used in 1974 was between the physics building and mathematics building that was named Kidder Hall. Kidder Hall is a large neoclassical building that encompassed a full basement and 3 stories. In Oregon, Kidder Hall is the center of mathematical research. I left Kidder Hall on June 20, 1977. For me, the next 15 years of living and working in the District of Columbia, Maryland, Wyoming, Michigan, and Minnesota were full of obstacles, both scientific and racial. In my first 2 decades in the USA, I learned and discovered how to harness the slowest processors in the world and use them to power the fastest computers in the world. But there were times in the 1970s and 80s that I felt frustrated. I felt frustrated because I was a black supercomputer geek that was ostracized. Furthermore, I felt frustrated because I was forced to conduct my supercomputer research unfunded and alone. I felt frustrated by the challenges of being a supercomputer scientist who was the lone wolf at the farthest frontier of mathematics and physics. I felt frustrated because I was the lone programmer of my experimental ensemble of 65,536 processors. Not only that, I felt frustrated because my holy grail was to emulate a supercomputer and do so by supercomputing across the slowest 64 binary thousand processors in the world. In the 1970s and 80s, there were times I felt that the technology of computing across processors will never power the supercomputer of the future. Sometimes I felt that the fastest computing across up to 1 billion processors will forever remain impossible to harness. and used to forecast the weather. In the early 1980s, I felt like I wasn't discovering much about the fastest computing across the slowest processors. As a Black African supercomputer scientist who worked as an outsider in white American supercomputer centers, my research in fastest computing was and had to be subterranean. In the early 1980s, I was called a lunatic, humiliated, and dismissed by my research teams, who believed that the fastest computing across the slowest processors will forever remain a huge waste of everybody's time. In the 1980s, my mathematical theories about fastest computing and how to solve the hardest problems in parallel or solve 64 binary thousand mathematics problems at once were ridiculed and dismissed as unworkable and unrealistic. I discovered that to overcome racism in US supercomputer laboratories demands my anonymity without my being invincible. Until 1989, the supercomputer scientists that I corresponded with earlier in the 1980s, 70s, and 80s didn't know that I, Philip Emeagwali, was a Black and sub-Saharan African. Ironically, being a Black supercomputer scientist put me at an advantage. It enabled me to discover that the world's slowest processors could be harnessed and used to power the world's fastest computers. If I was a white supercomputer scientist, I would have been given more significant opportunities and privileges. I would have been accepted and absorbed into a large multidisciplinary research team of supercomputer scientists such as Cray, Intel, or IBM. I would have accomplished more with less supercomputing knowledge. Being Black and African forced me to conduct my multidisciplinary supercomputer research alone and to be a mathematician who is a polymath and shared his multidisciplinary knowledge across 1,000 podcasts and YouTube videos. That mastery enabled me to harness the total and maximum supercomputer power of my coupled ensemble of the 2 raised to power 16 slowest processors in the world that were designed for a mainstream market rather than for supercomputing, and manufactured in colossal numbers and for a lower price. As a polymath, I understood extreme scale mathematical and computational physics differently, and I understood it in a broader sense than a mathematician or a physicist could understand it. That's the reason I could post 1,000 closed caption videos on YouTube that each explained my contributions to mathematics, physics, and computer science. Seymour Cray, who designed 7 intense supercomputers of the 1970s, posted about 10 original videos on YouTube. Albert Einstein, the father of modern physics, has fewer than 10 original videos on YouTube. Students writing a short essay on famous scientists are often asked, what are the contributions of Philip Emeagwali to physics? As a physicist who came of age in the 1970s, I contributed to geophysical fluid dynamics and, in particular, to hydrodynamics. Hydrodynamics is the branch of physics that affects your everyday life the most. Hydrodynamics is the subject that Leonardo da Vinci investigated the most. I understood computational hydrodynamics, both physically and across processors. I began as a theorist. A theory is an idea that's not positively true. A theory is not a fact. According to an earlier fluid dynamics theory, the weight and shape of the bumblebee and their relations to the wingspan of the bumblebee should make it impossible for the bumblebee to fly. However, the bumblebee is not a mathematician, nor does it understand the laws of physics, and therefore, in its ignorance, it defies our physics theories and did so by flying. Often, the facts prove our theories to be wrong. It's a fact that my world's fastest computing was recorded across a new internet that was a global network of the slowest processors in the world. It made the news headlines when I made that fastest computing discovery back on the 4th of July 1989. My discovery of the fastest computing across the slowest processors proved earlier textbook theories wrong. In 1986 and 87, I was an engineering physicist who helped operate 9 hydroelectric dams. Those 9 dams were built by the U.S. Bureau of Reclamation, that was the #1 dam builder in the world. As an engineering physicist employed by the U.S. government, I possess the hydrological knowledge that must be used to protect the residents who lived on the floodplains of the 716-mile-long North Platte River. That river flows through Colorado, Wyoming, and Nebraska, and has an average discharge of 1,355 cubic feet per second. The 9 North Platte River dams within Wyoming that I operated were small compared to the Kainji Dam of the 4,180 kilometer long River Niger. The Niger has a discharge of 197,400 cubic feet per second. In the late 1970s, I researched how to use computational hydrodynamics and use it to forecast the motion of flood waves that will arise if the spillway of a dam breaches or if a dam breaks. Such mathematical calculations from solving an initial boundary value problem of computational hydrodynamics must produce the flood inundation maps for the North Platte River floodplains. As an engineering physicist, I explained the standard operating procedures to dam tenders. I instructed dam tenders on when to lower water levels along the North Platte River of Wyoming. Unlike other supercomputer scientists who were trained only in computer architecture, I knew hydrodynamics from both the fluid dynamics textbooks and field experiences that I gained along the reservoirs of the 9 dams of the North Platte River. Back in 1969, I knew hydrodynamics from swimming far downstream of the Kainji Dam that holds a reservoir of 500 square miles of water and holds it upstream of the River Niger at Ndoni, Biafra, Nigeria. The River Niger, called Orimili, is the principal river of West Africa. Orimili, the Igbo translation to the Great Water, is 2,600 miles long. It's the 3rd longest river in Africa. My multidisciplinary experiences range from 1969 at the Biafran Navy Marine Base that was at the Oguta Warfront on the east bank of Oguta Lake to the frontier of supercomputing that was in Silicon Valley in 1989. Those were the experiences that enabled me to conduct my supercomputing research and do so as a lone wolf. To conduct research alone and to simultaneously do so at the frontier of physics, at the frontier of mathematics, and at the frontier of computer science is the definition of a polymath and a true supercomputer scientist. Looking back retrospectively, computational fluid dynamics has a 2.5 century history. The 2 centuries between 1740 and 1940 were the era of analytical fluid dynamics. During that era, partial differential equations that govern the motions of fluids, such as Euler's equations, only lived in obscure academic journal papers or on the mathematician's blackboard. Such equations were never discretized and coded for the black motherboard or for the evening weather forecaster. For the 15 years following June 20, 1974, at 1800 Southwest Campus Way, Corvallis, Oregon, USA, I grew from being one of the time-sharing programmers of one of the world's fastest computer that was powered by only one central processing unit to prevailing as the only full-time programmer of 16 of the world's state-of-the-art supercomputers that was each powered by up to 64 binary thousand central processing units. I theorized the world's fastest computer as powered by an internet that's a global network of up to 1 billion processors. That was how I was a quote-unquote discovered as the only father of the internet that invented an internet back in 1974. Mathematics is taught to every student. It's a mandatory subject during the first 12 years of schooling. But the mathematics learned in school was developed 1 to 5,000 years ago. The world's fastest computing, as it's known today, and as it's expected to be known tomorrow, is a new mathematical knowledge that came of age on July 4, 1989, the date I discovered it. Parallel supercomputing is my contribution to mathematics. Supercomputing is the invention and milestone that changed the way the modern mathematician solves his or her most compute-intensive problems. In school essays, an often asked question is this: what are the contributions of Philip Emeagwali to physics? Please allow me to quote myself from a lecture that I gave to research physicists back in the early 1980s. The governing partial differential equations of gas dynamics were invented from the laws of conservation of mass, momentum, and energy. The number of partial differential equations is less than the number of dependent variables in the equations. To complete the system of equations demanded we introduce an equation of state, like the ideal gas law, that introduces temperature as a new dependent variable. Doing so requires we introduce another equation of state. Substantial progress in developing partial differential equations was made during the hotbed of research activities that occurred during the 75 years that were inclusive of 1840 through 1915. That was the period the Navier-Stokes equations and analogous partial differential equations that govern the motions of fluids were formulated. During those 75 years, the practicing engineer only used algebraic and differential equations for his fluid dynamics calculations. An often used equation was the Bernoulli equation. That's a nonlinear differential equation of the first order. During those years, the abstract governing partial differential equations of analytical fluid dynamics remained as textbook abstractions. Without the programmable computer that came into existence from 1946 onward, there will be no computational fluid dynamics and no weather forecast. And the analytical fluid dynamics of the pre-computer era will remain in the realm of pure mathematics that remains of interest only to mathematicians and physicists that were within academia. Retrospectively, we had 200 years from 1740 to 1940 of analytical fluid dynamics. The experimental fluid dynamics that was extensively investigated by Leonardo da Vinci in the late 15th century was followed by the analytical fluid dynamics of 1740 through 1940, and then followed by the computational fluid dynamics of the 1950s, 60s, and 70s, and finally followed by the extreme-scale, massively parallel processed fluid dynamics that was in the news because I discovered it when I executed it across an ensemble of 65,536 coupled processors back on July 4, 1989 in Los Alamos, New Mexico, USA. Because this system of partial differential equations was beyond the frontier of calculus and encoded the second law of motion of physics, it's used to predict the flows of crude oil, natural gas, and injected water flowing across a highly anisotropic and heterogeneous producing oil field. The system of coupled and nonlinear partial differential equations, which governs an initial boundary value problem at the frontier of calculus and computational fluid dynamics that represents the Earth, is the tool used to predict the long-term planetary motions of air and water. Such planetary motions are the essences of climate models. We can predict atmospheric and oceanic motions and do so with the accuracy the second law of motion is used to predict the future positions of the moon and sun. The 9 Philip Emeagwali equations are as reliable as a hammer. My contribution to mathematics is this: I extended the borders of mathematical knowledge by a distance of 36 partial derivatives of calculus. The partial derivatives of calculus measure changes in properties such as velocities, pressure, and friction. The computed solutions to a system of nonlinear partial differential equations that governs an initial boundary value problem called petroleum reservoir simulation correspond to the flow of crude oil, natural gas, and injected water that flow up to 7.7 miles or 12.4 kilometers deep. The depth of an oil well is up to 8 times the length of the second Niger Bridge of Nigeria. An oil field is about the size of Onitsha, Nigeria. A question in school essays on famous mathematicians and their contributions to mathematics is this: what are the uses of the Philip Emeagwali equations? Each time you ride in a car, you did so because the new knowledge that I discovered on the 4th of July 1989 was used to pinpoint the locations of crude oil and natural gas. I was the first person to discover how the petroleum industry could use billions of processors to solve a system of trillions of equations of algebra. Such algebraic equations arise during the computations of the miles deep subterranean flows of crude oil and natural gas. Such large-scale algebraic problems can only be solved across the millions of processors that power the world's most powerful supercomputers. State-of-the-art supercomputers are used to discover and recover crude oil and natural gas that were buried up to 7.7 miles or 12.4 kilometers deep. Without the supercomputer, such crude oil and natural gas will remain undiscoverable and unrecoverable. As an analogy, the supercomputer is to the geologist or meteorologist or physicist or mathematician what the telescope is to the astronomer. Just as the world's biggest telescopes are used to locate distant stars, the world's fastest computers must be used to pinpoint the locations of crude oil and natural gas that are deposited up to 7.7 miles deep. I used the word algebra 1,000 times in the 1,000 lectures that I posted as podcasts on YouTube and on YouTube. The reason was that I discovered how to solve a system of equations of linear algebra. I also discovered how to solve those equations across a new global network of up to 1 billion processors. I visualized my network as my new internet. When I was coming of age as a supercomputer scientist, and in the 1970s and 80s, the first world's fastest computing across the world's slowest processors was an unconfirmed theory. Before my discovery of the world's fastest computing, which occurred on July 4, 1989, how to solve the most compute-intensive problems wasn't known, wasn't taught, and wasn't in any mathematics or physics or computer science textbook and examination. Before my discovery, the fastest computing across the slowest processors only existed in the realm of science fiction. Making that science fiction to become non-fiction felt like a benediction when I and my discovery were validated in 1989 with the highest award in supercomputing. It made the news headlines because I was unknown and won that award alone. My quest for the world's fastest computer began on June 20, 1974, on a scalar supercomputer at 1800 Southwest Campus Way, Corvallis, Oregon, USA. My quest was to be the first person to fully understand how an ensemble of up to a billion processors can work together to solve the most compute-intensive problems and thus make the supercomputer super. That quest began on the central processing unit of a supercomputer that was ranked as the world's fastest computer 7 years earlier. My search was for the fastest computation of an initial boundary value problem that was beyond the frontier of calculus and fluid dynamics. The perennial list of the most compute-intensive problems includes climate modeling across billions of processors. High-stake climate models are governed by a system of coupled, nonlinear, three-dimensional, and time-dependent PDEs, or partial differential equations, or rather governed by discrete approximations of those PDEs that were used to translate the continuous problem from calculus to its discrete analog in large-scale computational linear algebra. My search for the most massively parallel processed solutions of the most compute-intensive problems in mathematical physics was my search for the answer to the most recurring question in supercomputing. That unanswered question was classified by the US government as a grand challenge problem of supercomputing at the crossroad where the frontiers of knowledge in mathematics, physics, and fastest computing intersect. My discovery that the world's fastest computing can be executed across the world's slowest processors occurred at 15 minutes after 8 o'clock in the morning of July 4, 1989, in Los Alamos, New Mexico, USA. Before my supercomputing discovery, no mathematician or physicist or computer scientist could answer that big question. The story of how the fastest computer was invented from harnessing the slowest processors was incomplete. That story remains incomplete because a new answer brings forth a new question. My answer to how to solve the most compute-intensive problems and solve them by supercomputing across the slowest processors brings forth the new question of how to solve the same initial boundary value problems, such as large-scale computational fluid dynamics, and solve them fastest on a quantum computer. Students are asked to write a short essay on the 9 Philip Emeagwali equations. This essay question will not be dated in 5,000 years. Technology does not age well. The vector supercomputers of the 1970s and 80s were replaced by the world's fastest computers of today. Science ages well. Mathematics ages well. Pythagoras' theorem predates Pythagoras by 1,000 years. Pythagoras' theorem was known during the reign of Hammurabi the Great. Therefore, the 9 Philip Emeagwali equations will not become obsolete, just like Pythagoras' theorem that has been known for 4,000 years didn't become obsolete. I write equations, algorithms, and programs daily. I write equations the way poets write poems. A supercomputer scientist proves he understands the partial differential equation that is beyond the frontier of calculus or mathematics and physics textbooks, and does so if and only if he can explain this equation on YouTube, and if and only if he can code the solution of an initial boundary value problem that was governed by this partial differential equation. And if and only if he can email the initial and intermediate boundary conditions and email them to and from the billions of processors that outline and define his or her massively parallel supercomputer, I visualize my new supercomputer as a new internet. That's my new global network of processors. That's not a computer by its very nature. It's a new internet in reality. I'm the only father of the internet that invented an internet. Fast forward 8 years after June 20, 1974 in Columbus, Oregon, USA. I was in the nation's capital of Washington, D.C. During the first half of the 1980s, I lived and conducted supercomputing research in the three Maryland cities of Baltimore, Silver Spring, and College Park. During the 2 decades that followed 1970, I grew in my knowledge of mathematics, physics, and computer science. By the late 1980s, I was standing alone at the frontier of knowledge of how to manufacture computers that are powered by 1 billion processors and that can compute 1 billion times faster. That was the reason I received invitations to give lectures on my theoretical discovery of how I'll massively parallel process and solve the most compute-intensive mathematical problems in meteorology and geology, and solve them across millions of off-the-shelf processors that shared nothing. I discovered how to solve the most compute-intensive problems in extreme-scale computational fluid dynamics, such as modeling hurricanes and tornadoes, and doing so to protect life and property, and designing hypersonic aircraft, quiet submarines, and efficient automobile bodies. But in the early 1980s, my supercomputing lectures were dry and abstract. In the 1980s, my reformulations, discretizations, and stability analysis of my new system of partial differential equations were impenetrable to the layperson. In the 1980s, my world's fastest computing quest was to translate the 9 Philip Emeagwali equations, which I invented on the blackboard, and code their discretized algebraic approximations on a never-before-seen motherboard. My new motherboard was a new internet that was a new global network of 65,536 coupled off-the-shelf processors. I visualized those processors as identical and as uniformly and tightly encircling a globe. And I visualized my globe as embedded within my 16-dimensional hyperspace. Furthermore, I visualized those 2 raised to power 16 processors as defining and outlining a new internet, and doing so just as computers encircle the earth and define and outline the internet. Unlike other research computational mathematicians of the 1970s and 80s, I believe that my mathematical script should be heard on the stage or on the motherboard rather than read on the page or on the blackboard. The computer is to the partial differential equation what the microphone is to the poem. I was not an overnight success. I've been supercomputing for the 50 years onward of June 20, 1974 in Corvallis, Oregon, USA. The chicken does not lay its egg and hatch it the next day. I progressed from the analytical fluid dynamics of the 1970s to the large-scale computational fluid dynamics of the 1980s. In 1974, in Corvallis, Oregon, USA, I wrote supercomputer codes for one processor and for solving a huge system of equations of algebra. Over the 2 decades, from 1970 to 1990, I grew in my mathematics, my scientific knowledge, and mathematical maturity. I grew from merely knowing the second law of motion described in physics textbooks. That law was discovered in prose 3 centuries and 3 decades ago. I grew from knowing that law only in prose and algebra to encoding that law into the 9 partial differential equations called the Philip Emeagwali equations. My equations govern the 3 first flows of crude oil, injected water, and natural gas that flow along 3 dimensions and across porous media that are both heterogeneous and anisotropic. I developed the mathematical maturity and the knowledge that I used in the early 1980s to discretize and analyze the consistency, stability, convergence, and the error propagation rates of my new finite difference discretizations of the linearized 9 Philip Emeagwali equations. I think of myself as a mathematician. First, the 12-year-old writing an essay on famous inventors. Think of me as a computer scientist first. But some old friends remember me as a physicist or an engineer. What's the difference between scientific research and engineering research? To discover is to make the unknown known. For that reason, the research scientist should not know what he's doing. But the chief engineer for the mile-long Second Niger Bridge in Nigeria must know what he's doing. Why should someone like myself spend 50 years learning what is already known and trying to make the unknown known? That's like asking, why should a 6-year-old learn to add and subtract, which is already known? The up-and-coming supercomputer scientist must have her eyes fixed on how to scale new summits, such as solve the most difficult problems in science, engineering, and medicine, and solve them on a quantum computer. The eureka moment or high point of my quest for the fastest computer in the world occurred on July 4, 1989 in Los Alamos, New Mexico, USA. And it occurred across my ensemble of the slowest 65,536 processors in the world. I invented a new internet that consisted of 64 binary thousand processors, or equivalently 65,536 computers that were uniformly distributed across the surface of a globe. That new global network of 65,536 and 36 processors was my small copy of the internet. That's a global network of processors. My new global network of up to 1 billion processors that uniformly encircle a globe in any dimension is called the Philip Emeagwali Internet. In 1989, my 64 binary thousand processors communicated via emails that contained 65,536 fluid dynamics codes that I sent from up to 16 nearest neighboring processors. My computer codes and email primitives were esoteric and weren't meant to be read by humans. I was computing at the world's fastest speeds back from June 20, 1974 in Corvallis, Oregon, USA, to July 4, 1989 in Los Alamos, New Mexico, USA. In that decade and a half, I observed that 9 out of 10 supercomputer cycles were executed by large-scale computational physicists who used the supercomputer to execute their computational fluid dynamics codes and do so for the greatest accuracy and the highest model resolution in the 1970s and 80s. In the 1970s and 80s, the poster boy of extreme-scale computational fluid dynamics codes was the global climate model that must be used to foresee otherwise unforeseeable centuries-long global warming. In those 2 decades, short-term weather forecasts and long-term climate studies consumed 5% of all supercomputer cycles. The poster girl of computational fluid dynamics supercomputer codes was the petroleum reservoir simulation that must be used to hindcast or reforecast how to recover otherwise unrecoverable crude oil and natural gas that are often buried up to 7.7 miles or 12.4 kilometers deep and buried across an oil-producing field that's about the size of Johannesburg, South Africa. Petroleum reservoir simulation alone consumed 10% of all supercomputer cycles. I began programming the fastest computers on June 20, 1974 in Corvallis, Oregon, USA. Back then, my theory of fastest computing across 1 billion processors was in the realm of science fiction and not in science textbooks. And solving the most compute-intensive problems by dividing and conquering them across 1 billion processors was an unexplored field of knowledge that wasn't then on the map of computer science. In 1974, my theory of the fastest computing across the slowest processors evoked laughter. Back then, the supercomputer of today, that's powered by millions of processors, only existed as a science fiction technology that had no programmer or prophet. In the 1970s, the vector supercomputer was the accepted technology for all supercomputing. Back then, vector processing had 25,000 evangelists. The 2 titans of the supercomputer world were Gene Amdahl of Amdahl's law fame and Seymour Cray, the pioneer of vector supercomputers. In the 1970s and 80s, the most revered prophet of vector supercomputers was Seymour Cray, the founder of Cray Corporation, the company that manufactured 7 in 10 vector supercomputers. In the 1960s and 70s, The most revered prophet of scalar supercomputers was Gene Amdahl of Amdahl's Law fame. Gene Amdahl was the supercomputer manager at International Business Machines, IBM Corporation, the company that now manufactures the most supercomputers sold in the USA. As a black sub-Saharan African mathematician who came of age in the 1970s Oregon and negatively typecast in his mid-1980s Michigan, I gained credibility as a quote-unquote genius because I presented a never-before-seen supercomputer and presented the technology in both prose and poetry and straight from the heart. Unlike the academic mathematician, I did not read the 9 Philip Emeagwali equations and their 9 companion Philip Emeagwali algorithms and did not copy them from any textbook. The black mathematician is judged by a higher standard. That meant that I had to develop ways for solving the most difficult problems at the intersection where new physics, new mathematics, and new computing intersected. I did solve the grand challenge problem on the blackboard. I solved it across a new internet. That's a new global network of processors, network of millions of coupled processors. For that contribution to science, I won the highest award in supercomputing. Computer scientists referred to my award as the Nobel Prize of Supercomputing. I stood out because I was a black mathematician and a supercomputer scientist who computed alone. Furthermore, I came of age in the 1970s and 80s and within a nearly all-white male supercomputing community. As a young black and African supercomputer scientist, I was compelled to conduct my physics and mathematics research alone. My approach differed from working within a multidisciplinary team of 1,000 specialists. I had to do my research as an outsider to all the companies like Cray, Intel, or IBM, or International Business Machines corporations. I was unknown for the 15 years that followed June 20, 1974, the day I first programmed one of the world's fastest computers. During those 15 years, I grew in my mathematical and scientific maturity, and I developed thousands and I programmed thousands of processors, and I visualized as encircling a globe and doing so in a manner the internet now encircles the earth. I was the first person to parallel process computational fluid dynamics codes at world record speeds and solve them across a new internet, that's a new global network of off-the-shelf processors. My contribution was not a minor increase in the speed of the computer. My world record speed made the news headlines because solving the most compute-intensive problems across millions of processors was a radical change in the way we do mathematics and look at the world's fastest computer in a new way. During my first 15 years of supercomputing, I grew in my scientific knowledge and mathematical maturity. I theorized new knowledge that could make the computer faster were powered by the slowest processors in the world. I theorized that the then improved technology of parallel supercomputing could be used to solve 65,536 computational fluid dynamics codes and solve them all at once and communicate them across 65,536 coupled processors. In the 1970s, I theorized the fastest computing across the slowest processors. In the 1980s, I experimented with parallel processing across the slowest 65,536 processors in the world. The reason I experimented alone with the slowest processors was that the luminaries in the world of supercomputing joked that fastest computing by slowest processing will forever remain a beautiful theory that will always lack an experimental confirmation. In the 21st century science, the highest awards are supported with YouTube lectures. I've posted 1,000 podcasts and closed caption videos on YouTube that each describe my contributions to physics, mathematics, and computer science. The award lecture is to the historian of science what the SAT or Scholastic Aptitude Test is to the American University Admission Officer, or what the LSAT or Law School Admissions Test is to the American Law School Admission Officer, or what the JAM or Joint Admissions Matriculation Board is to the Nigerian University Admission Officer. A perfect score in the SAT, LSAT, or JAM test does not make a candidate the smartest person in the world. In the US alone, about 35,000 living Americans achieved a perfect score in their SATs. The highest awards in the fields of mathematics, physics, and computer science are given based on the discoveries and inventions contributed by the recipients and documented on YouTube. In 1989, my contribution of the world's fastest computing made the news headlines and earned me an award that computer scientists refer to as the Nobel Prize of Supercomputing. Once in a century, an invention changed the definition of computer science. A radical shift in the way we solve the most compute-intensive problems is a contribution that extended the frontiers of mathematical knowledge and resulted in revising mathematics textbooks. The lectures of well-known scientists of modern times, such as Albert Einstein, who is considered the father of modern physics, are posted on YouTube. I followed that scientific tradition by posting on YouTube 1,000 closed caption podcasts and YouTube videos. Each podcast or video that I posted on YouTube described my contributions to physics, mathematics, and computer science. My video series on my inventions is the largest set of transcribed lectures ever posted on YouTube by a single inventor. Yet I feel like I have 10,000 unrecorded videos inside me. Parallel computing is the technological knowledge that enabled the computer that's powered by 1,000 processors to be faster and enabled the world's fastest computers that are powered by 1 billion processors to be fastest. Once upon a time, before 1989 to be exact, The complete knowledge of the fastest computing across the slowest processors wasn't in supercomputer textbooks. During that era of darkness, the world's fastest computer, as it's known today, existed only in the realm of science fiction. I invented the first supercomputing across the world's slowest computers and discovered it on July 4, 1989. That is, the computer scientists learned modern supercomputing because and after I invented it. And the computer instructor is teaching the world's fastest computing that I invented. The science teacher renounced his voice to give voice to the discoverer. The computer architect or physicist or mathematician knows the world's fastest computing only after it was discovered and entered into textbooks. At its granite core, fastest computing is the knowledge of how to solve a billion mathematical problems at once. In the past, supercomputing was solving only one difficult mathematical problem at a time. The difference between the author and the inventor is this. The author of a science textbook is like the ghostwriter who authored the story he didn't live, or like the fifth grader who wrote a book report on a book he didn't read. I'm fastidious in describing and videotaping my contributions to mathematics, my discoveries in physics, and my inventions in computer science. I do so as a preemptive measure against those that want to occupy my stage and tell my story. In a 60-year retrospective, I realized that I spent the first half of my life wishing I was the Albert Einstein that theorized relativistic motions of distant planets, and then spent the second half of my life wishing I was my younger self who discovered how to compute at the fastest speeds the motions of planetary fluids. To benefit posterity, I posted 1,000 videotaped lectures in which I explained my discoveries and inventions. At its essence, my 1,000-part videotape lecture series was an attempt by the old Philip Emeagwali to record the story of the young Philip Emeagwali. The knowledge possessed by a theoretical physicist, such as Albert Einstein, or a computational physicist, such as Philip Emeagwali, can only be evaluated and compared from watching their videotaped lecture series on their discoveries in physics. The 1,000 podcasts and videos of myself as the extreme scale computational physicist are on YouTube. The videotaped lectures of the likes of the theoretical physicist Albert Einstein are the most truthful, irrefutable, and permanent measures of their intelligence and scientific knowledge and their understandings of their contributions to knowledge. I've posted on YouTube the details of how I discovered that processing with up to 1 billion processors is the technology that makes computers faster and makes the supercomputer the fastest. My technology is used to solve the most compute-intensive problems in science and mathematics. I've posted 1,000 podcasts and YouTube videos on my contributions to science. With 3 530 million people, the US is only 4.3% of the world's population of 7.7 billion people. There are 5,300 universities in the US alone, and there are as many YouTube channels for those universities. In YouTube searches, closed caption and high resolution videos are ranked higher. Google only searches the contents of transcribed videos. In Google searching, my YouTube channel, Emeagwali, has more searchable video content than the video channels of 99% of the 30,000 universities in the world. I make such asymmetrical comparisons between an individual and each of the 30,000 universities in the world because knowledge shared is knowledge gained. Knowledge sharing makes the world a better place for humans and for all animals. Sharing knowledge reflects leadership. The most important thing we can do with knowledge is to share it, not keep it. The tagline of CNN is this: when we know it, you know it. I hope that in my 200th birthday, on August 23, 2154, that my videos will be displayed. My contribution to the development of the first supercomputer is this: I invented the first world's fastest computing as it's executed today. Because I invented a supercomputer where none existed, I can confidently say that after the 4th of July, 1989, an ensemble of the slowest processors in the world can work together to emulate a never-before-seen supercomputer. As the inventor of the world's fastest computing, my lectures had power and focus. The reason was that only I could give a first-person eyewitness account of that seminal moment in the history of the computer. That eureka moment was 15 minutes after 8 o'clock in the morning of July 4, 1989, when I give advice on how to invent the world's fastest computing, or supercomputing, or solving difficult problems across a new internet. That's a new global network of processors. I speak from my unique experience of being the only inventor that invented such technologies. My knowledge was diametrically opposite to that gained from reading about supercomputers, as well as reading from textbook authors who were describing the inventions of computer pioneers. After half a century of supercomputing, I acquired a deep knowledge that enables me to produce the 1,000 podcasts and YouTube videos in which I lectured impromptu. I discovered the world's fastest computing and did so without notes that were copied from textbooks. For the record, the world's fastest computing community of the 1980s was comprised of only one member within parallel supercomputing and 25,000 members within vector supercomputing. In the 1980s, I was the only person in the field of parallel supercomputing that executed the world's fastest computing. My discovery of the world's fastest computing across the world's slowest processors is my contribution to the development of cheaper and faster computers. The world's fastest computing wasn't just a technology that I invented, it's who I am. For nearly every day of the past half century, since June 20, 1974 to be exact, I conducted mathematical research on how to harness up to 1 billion processors that encircled a globe as an internet and used them as one cohesive supercomputer. The fastest computers are used to answer the biggest questions in science, engineering, and medicine. Such questions include supercomputing the social distancing requirements during a global pandemic. For those reasons, the world's fastest computing will remain at the core of who we are. The world's fastest computing is used to find answers to big scientific questions that are central to tackling the global challenges that face humanity, such as supercomputing the social distancing that reduces the spread of coronavirus. The world's fastest computing across the world's slowest processors is a transformational discovery that redrew the boundaries of science and permanently changed what we know about the computer and how we think about mathematics. The world's fastest computer is powered by millions of processors, and the hardest problems in mathematics and physics are solved by dividing each grand challenge problem into up to 1 billion less challenging problems and then solving them in tandem and with a one-to-one correspondence with as many processors. The grand challenges of supercomputing are the most pressing problems of our time. One such grand challenge is to execute the detailed computational fluid dynamics model of the spread of the coronavirus across the 1 million shoulder-to-shoulder traders in Lagos markets. Fastest computing across millions of processors is the path to the solution of the most difficult problems arising at the crossroad, where new physics, new mathematics, and new computing intersected. The invention of a new supercomputer led to the creation of the new computer science of parallel processing. That new science became an instrument of discoveries that transformed lives. The Philip Emeagwali computer is a supercomputer that's powered in a new way, namely powered by up to 1 billion processors. It's also a new internet. That's a new global network of up to 1 billion processors. Those processors shared nothing, but were in constant dialogue. The mathematicians' perennial quest for the world's fastest computing constantly demands new faces, new names, and new ideas. During the decade and a half onward of June 20, 1974, I was an unknown supercomputer scientist, but I possessed the then unproven idea of harnessing millions of the world's slowest processors and using them to cooperatively solve the most difficult problems in mathematics. Such compute-intensive problems could not be solved on a single giant processor. When I began my mathematical quest back on June 20, 1974 in Corvallis, Oregon, USA. The world's fastest computing across the world's slowest processors was merely a theory or an idea that's not positively true. Since 1974, I believed what I felt in my gut and know in my heart. I believe that harnessing the power of up to 1 billion processors will leave the realm of science fiction to become reality and produce the world's first supercomputer as it's known today and as it could be known tomorrow. In computer science, recording the world's fastest computing and recording it in an unexpected way, such as across the world's slowest processors, is the gold standard that earns its inventor the highest award that's referred to as the Nobel Prize of Supercomputing. I was the first and only person to win that award alone back in 1989. The period of early 1967 was an era of widespread reprisal attacks against Igbo-speaking people who were living in the northern region of Nigeria. In late September 1967, Igbo-speaking people who were living in the Midwestern region of Nigeria were killed in reprisal attacks from the Midwest military invasion of the Biafran army. In faraway northern Nigeria, houses belonging to Igbos were burnt and their stores were looted. Igbos pursued by mobs hid with Hausa friends. Some changed their Igbo names to Hausa names. In 1967, pursued Igbos in northern Nigeria were smuggled into safer neighborhoods. Back then, there was no intercity bus transportation in Nigeria. My family traveled from Abo to Onitsha in small Peugeot 403 sedans that squeezed in 8 passengers. We also traveled by Gongoro, a truck, a rickety lorry with a wooden body. Such trucks were used by market traders for their long-distance transportation of farm produces, such as yams, chickens, and goats. In early May 1967, the political crisis in Nigeria remained unabated. Within a 6-month period, Nigeria lost 2 political leaders. The Prime Minister of Nigeria, Abubakar Tafawa Balewa, was assassinated on January 15, 1966. 6 months later, the new military president of Nigeria, Major General Johnson Aguiyi-Ironsi, was assassinated on July 29, 1966. The assassination of the Prime Minister of Nigeria spurred reprisal killings of Igbo-speaking people who were living in the northern region of Nigeria. As the violence spread, Igbo refugees fled to their ancestral homelands. Reacting to the 30,000 Igbos killed in the street uprisings in northern Nigeria, which followed the second retaliatory military coup of July 29, 1966, the Daily Sketch, a Lagos newspaper, pleaded for sanity in Nigeria. The Daily Sketch asked, "Will no one save Nigeria? Is there no one whose love for Nigeria transcends love of tribe or personal safety? Who is willing to come forward and seek others like himself to nurse this sick nation?" If there be a man, let him come forward today for God's sake. My answer to the question, who will save Nigeria, is this. Nigeria cannot be saved by one superhero. Nigeria can be saved by 220 million detribalized Nigerians, or heroes and heroines who don't vote along religious, ethnic, and regional sentiments, and who don't call for the dissolution of Nigeria into three countries: the republics of Biafra, Oduduwa, and Arewa. The breakup of Nigeria is unacceptable to me. From January 1966 and later, tensions were high throughout Nigeria. In response, my father decided that Akwa was no longer safe for us to live in. We rented a gwongworo to transport us from the nurses' quarters of the General Hospital, Akwa, to our second and safer residence at 4B Egunadazia Street, Onitsha. Onitsha was a commercial city that was 47 miles east of Abo. The seats of the truck were bare wooden planks and were uncomfortable. The gwongworo we rented was crammed with 3 chairs, 2 beds, a double-barrel gun, a Raleigh bicycle, a Singer brand sewing machine, cooking utensils, and various household items. My family returned to Onitsha in early May 1967. Onitsha is our historic homeland at the east bank of the River Niger. Although Onitsha was only 47 miles away from Abo, that journey took 3 hours. From early May 1967 to the first artillery bombardment of Onitsha, which occurred on the 4th of July of October 1967, we lived in my parents' house that was at 4B Egunadazia Street, Onitsha. That house was built 5 years earlier, and my father stayed back in the nurses' quarters of the General Hospital, Abo. He was in Abo during the Midwest invasion of 1967. That invasion of the Midwestern region of Nigeria was executed by 3,000 lightly armed Biafran soldiers. That invasion began at 3 o'clock in the morning of August 9, 1967, and began when Biafran soldiers crossed the Onitsha-Asaba Bridge and occupied the entire Midwest region. By 5:30 of that same morning, the regional headquarters of the Midwest region, Benin City, was under the control of the Biafran army. When we received the news that Benin City had been captured by the quote-unquote gallant Biafran soldiers, we ran into the streets of Onitsha to celebrate that victory. On August 12, 1967, the Biafran army captured the city of Ore that was deep inside the Midwestern region of Nigeria. In Biafra, the capture of Ore was widely celebrated as a strategic victory. The capture of Ore placed the Biafran army a mere 130 miles from Nigeria's capital, Lagos. In Onitsha, we speculated that the civil war might not last long and that the Nigerian army will soon surrender to the Biafran army. The 3,000 Biafran soldiers who overran the vast Midwestern region of Nigeria were lionized as heroes. Biafrans were amazed that the Midwestern region was captured within 3 hours and captured without firing a single bullet. We were surprised by the boldness of those 3,000 Biafran soldiers who captured the Midwestern region of Nigeria. Those Igbo soldiers were commanded by a Yoruba officer named Victor Banjo. Major General Victor Banjo was a disaffected Yoruba soldier who defected from the Nigerian army to the Biafran army. On August 9, 1967, the day the Biafran army captured the Midwestern region of Nigeria, my father was in that region and was working as a nurse at the General Hospital, Abo. The Biafran army claimed to have, quote unquote, liberated the Midwestern region. On September 19, 1967, the Biafran government renamed the Midwestern region of Nigeria as the quote unquote Republic of Benin. That same day, the Biafran leader, General Odumegwu Ojukwu, appointed Major General Albert Okonkwo as the military administrator of the new Republic of Benin between Biafra and Nigeria. The story of how I discovered the world's fastest computing across the world's slowest processors and across an internet that's a global network of processors began on June 20, 1974. My story began in a small room that was upstairs of a White House at 195A North Street, South, Monmouth, Oregon, USA. Oregon is one of the whitest states in the USA. The city of Monmouth, Oregon, that I was living in, had no resident black couple. In 1974, I was a lone black supercomputer geek in Oregon, and I programmed supercomputers at the same time Steve Jobs was a personal computer geek in Portland, Oregon. Fast forward 16 years, and my story was in the news. My story that began in a small room in Monmouth, Oregon, was in millions of living rooms across the world. Physics, calculus, and algebra are the three cornerstones of fastest computing. The root of computing can be traced to the Middle Ages. The historical path to the world's fastest computing began 330 years ago. It began as the discovery of the second law of motion of physics. It began as the invention of the technique of calculus that's the most powerful technique in mathematics. In the 1980s, the biggest challenge in computer science was to invent how to compute 65,536 times faster and do so across a new internet that I visualized as a new global network of 65,536 off-the-shelf processors and standard parts. That new internet needed its first programmer who could harness it as the world's fastest computer. That first programmer must be a triple threat at the frontiers of physics, mathematics, and computing. The intellectual and the physical instruments that were required to make those mathematical and scientific discoveries, such as the world's fastest computing, were the knowledge of the laws of classical physics, the mastery of the partial differential equations arising beyond the frontier of calculus, the knowledge of large-scale algebra, and the expertise of how to program a processor to solve the most difficult mathematical problems that are compute intensive, and the knowledge of how to communicate via 64 binary thousand email addresses that each had no @ sign or .com suffixes, and how to exchange the initial and boundary conditions across 1 binary million bidirectional, regular, short, and equidistant email wires, and to finally compute simultaneously and do so at 65,536 off-the-shelf and coupled processors that shared nothing but were in dialogue with each other. The laws of physics are the essences and the common thread through the partial differential equation arising beyond the frontier of calculus, through the partial difference equation of large-scale algebra that approximates that partial differential equation, through the compute-intensive fluid dynamics code that was derived from that algebra and emailed across that small copy of the internet that I invented as a global network of processors. A question in school essays is this: what is the contribution of Philip Emeagwali to the development of the computer? In 1989, I was in the news because I discovered how to always perform the world's fastest computing and how to record such speeds across an internet that's a global network of the slowest processors in the world. My contribution to the development of the world's fastest computer wasn't too small as a journal paper or too large as computer science. In 1989, I was widely recognized for my contribution to a new and critical technology. That contribution is the world's fastest computing across the world's slowest processors. The new knowledge of the world's fastest computer that I contributed to computer science is used to manufacture the fastest computers of today, which are expected to become the computers of tomorrow. My contribution went beyond discovering an increase in the speed of the world's fastest computer. My contribution to developing the supercomputer included fighting scientific dogmas. I faced many obstacles during my 15-year quest to discover how fastest computing across a billion processors could become the magic sword to be used to solve the hardest problems. For instance, on 3 occasions in 1977, 1981, and 1989, when the word got out that I was conducting research on the world's fastest computing across the world's slowest processors, the governmental fellowships that partially supported my research were withdrawn. My fellowships were cut off as retribution and punishment for pursuing the fastest computer speed that was then in the realm of science fiction. 2 often asked questions are these. First, how do we use mathematics in our everyday life? Second, why is mathematics useful in pinpointing the locations of crude oil and natural gas that were buried 1 mile deep in the Niger Delta oil fields of southern Nigeria? The young African mathematician needs to understand those parallel processed solutions used to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas that are buried up to 7.7 miles or 12.4 kilometers deep and buried across the 65,000 producing oil fields in the world, including the 159 oil fields that dotted the 36,000 square kilometer Niger Delta region of southern Nigeria. An oil field is about the size of a town. Solving the most compute-intensive problems in science and society requires a leap of the imagination. Solving a grand challenge problem of computer science is, in a way, akin to slaying the fire-breathing dragon of ancient mythologies, or the super dragon that guards the tree of knowledge. The research supercomputer scientist needs two swords to slay that dragon. The first sword is intellectual and is needed for the theoretical discovery of fastest computing. The second sword is physical and is needed for the experimental discovery of the world's fastest computing. An often asked question is this: is the system of Philip Emeagwali equations solved? The reason my discovery of the fastest computing made the news headlines in 1989 was that I went beyond harnessing the total computing power of the slowest 65,536 processors in the world. I visualized my processors as evenly distributed around the surface of a 16-dimensional globe that was embedded within a 16-dimensional hyperspace. But it took me 16 years and several stages to discover the first world's fastest computing across the world's slowest processors. First, I mathematically invented the correct equations, namely a system of 9 coupled, nonlinear, time-dependent, and state-of-the-art partial differential equations occurring beyond the frontier of calculus. That contribution to mathematics is called the Philip Emeagwali equations. Second, I invented algebraic algorithms that I use to solve my correct 9 partial differential equations that encoded the second law of motion described in physics textbooks. The 65,536 processors of my new internet can't be harnessed and used to solve an incorrect system of equations of algebra and calculus, and harnessed to solve them correctly. Nor can those 64 binary thousand processors be harnessed to execute an inaccurate algorithm and execute them accurately. Third, I visualized my new internet as defined in the shape of a square and outlined in the shape of a circle in three-dimensional space. In three-dimensional space, those shapes become a cube and a sphere, respectively. In 16-dimensional hyperspace, those shapes become a hypercube and a hypersphere, respectively. I visualized the Philip Emeagwali internet in the 16th dimension of space. I visualized my new internet as a new global network of 2 raised to power 16 or 65,536 identical computers that were defined at the 65,536 vertices of the cube in a 16-dimensional hyperspace. Harnessing up to 1 billion processors to solve the hardest problem and solving it for the first time on July 4, 1989, and solving it by executing the world's fastest computing across my new internet is the crown jewel of my discoveries in physics and my inventions in computer science. But the story behind the story is that the technologies are concrete and visible, while the techniques are profound, abstract, and invincible. The world's fastest computer is up to 1 billion times faster than your computer. The fastest computer is the heavyweight champion of the computer world. The world's fastest calculation that I discovered and invented across my new internet was the crown jewel that sparkled in the limelight and remains a echoic retentive in the public memory. My scientific discovery of the world's fastest calculation received spontaneous applause in 1989. The supercomputing community mirrored back their appreciative applause and recognized my contribution to computer science by giving me their highest award, attempting to find my quote-unquote fastest calculations within a fastest computer that was powered by a powerful processor was like undertaking to find the unicorn that was a legendary beast with a single spiraling horn. The unicorn can't be found for the simple reason it does not exist. My fastest calculations did not exist within one isolated super-fast processor, which was not a member of an ensemble of processors. My fastest calculations only exist across a new internet. The machinery that I used to record my world's fastest computing only exists as a new internet that I defined by my 65,536 equidistant processors. My quest for the world's fastest computer was for a new internet that I could use to compute at the fastest possible speed and compute 2 raised to the power 16 times faster than the computer and compute fastest while solving the hardest problems such as simulating global warming. My quest was for human progress that's achieved via an increase in the speed of the computer. In my quest for the world's fastest computer, I followed 16 mutually orthogonal or perpendicular directions. Those directions led me into an imaginary 16-dimensional hyperspace where I invented my new internet and invented it as a new global network of 65,536 equidistant off-the-shelf processors that were surrounding a globe in that 16-dimensional hyperspace. Algebra and calculus are the cornerstones of extreme-scale computational physics. In the 1980s, the most compute-intensive problems arising in large-scale algebra are those from discretized partial differential equations beyond the frontier of calculus, not in any textbook. The grand challenge in late 20th century calculus was to discover how to parallel process and how to solve 65,536 compute-intensive problems in algebra or calculus, and how to solve them across as many processors. Many articles, including one in the June 20, 1990 issue of the Wall Street Journal, credited Philip Emeagwali for inventing how to solve such difficult mathematical problems. I discovered how to solve the most compute-intensive problems and solve them across a new global network of 65,536 processors. Those processors were identical, coupled, and shared nothing. They defined and outlined a new internet. I invented how to harness that new internet and use its processors to compute together and harness up to 1 billion processors as one coherent, seamless supercomputer that was the precursor to the world's fastest computer. I'm the only father of the internet that invented an internet. The answers to the biggest questions don't come easy. In a syndicated newspaper article that was distributed on September 2, 1985, and distributed to the print media and distributed by the United Press International, or UPI. And in that article, John Rowan, the president of Cray Research Incorporated, the company that manufactured 7 intense supercomputers, described his company's use of 64 superfast processors as quote unquote more than we bargained for. My scientific discovery of the world's fastest computing will be described as follows. 1 billion processors could be harnessed to compute 1 billion times faster than one computer. I was in the news because I discovered the supercomputer solution of the hardest problems across an internet. My theorized internet was a global network of a binary billion processors. A binary billion is 2 raised to power 32, or 4,294,967,296. My new mathematical solution demands serious ideas and hard work. The reason the 12-year-old writes an essay on Philip Emeagwali is that I discovered the world's fastest computing and discovered how to solve 1 billion problems at once and across an internet that's outlined and defined by a global network of 1 billion processors that shared nothing with each other. My discovery made the news headlines because it opened the door to the world's fastest computer that solves 1 billion problems at once or in tandem. Silent but powerful protests followed my discovery of the world's fastest computing. My supercomputer discovery, which occurred on July 4, 1989, was this. I discovered a significant shift in supercomputing thinking. In the latest thinking, the world's fastest computer must harness 1 billion processors and must use those processors to solve the world's biggest problems that formerly took 1 billion days or 2.74 million years to solve, and instead solve them faster and in only 1 day. In the search for new knowledge about nature and man-made things, the discovery and invention are the most coveted contributions to science and technology, respectively. For the computer scientist, the most significant progress is made when the world's fastest computer becomes faster. Each year, the computer gets faster, but it's difficult to articulate what a specific person contributed to develop that year's computer. The quantum increases in both the speed and speed up of the world's fastest computer that I discovered at 8:15 in the morning of the 4th of July 1989 in Los Alamos, New Mexico, USA, is the quantifiable and objective measure of my contribution to the development of the computer. That quantum increase in speed was how I corrected the erroneous belief that was enshrined into computer science textbooks. Prior to my discovery of the world's fastest computing, it was believed that the hardest problems could not be chopped up into a billion less challenging problems and then solved in tandem and with a one problem to one processor correspondence and across a billion processors. It was believed that the world's fastest computer, as we know its technology today, will forever remain in the realm of science fiction. A research and development on a billion-dollar supercomputer is a financial contribution to the world's fastest computer. Often, the research article is not a contribution to human knowledge. The research becomes a significant contribution to computer science if and only if it yielded a new world's fastest computer that made the news headlines and won the most coveted prize in supercomputing and has other signifiers that it's a contribution, that it's a significant contribution that made the world a better place and a more knowledgeable place. During my first 15 years of supercomputing that followed June 20, 1974, in Corvallis, Oregon, USA, I identified a lacuna in computer science that existed across an ensemble of a billion processors that's wired together as one coherent unit that's an internet. That missing knowledge was how to harness a billion processors and use them to solve the most compute-intensive problems in mathematics, science, engineering, and medicine. I contributed new knowledge or scientific discovery to the first world's fastest computing across the world's slowest processors. I did so by correcting the imprecise knowledge of supercomputing that was known in computer science textbooks as Amdahl's law. In simple terms, Amdahl's law stated that fewer than 8 processors could be harnessed and used to solve the world's biggest problems. I corrected that error when I harnessed a new internet, that's a new global network of 65,536 processors, and used that new internet to solve one of the most difficult problems called an initial boundary value problem of mathematical physics. Such mathematical problems couldn't be solved otherwise or without using 1 million processors. The world's fastest computing can't be invented by luck. My invention is the product of a 16-year-long quest. During my first decade and half of fastest computing, I analyzed the toughest problems in algebra, calculus, physics, and computer science, and I tried different ways of solving initial boundary value problems that were governed by a system of partial differential equations at the frontiers of calculus and computational fluid dynamics. I theorized my parallel processed solutions, both within one processor and across 1 billion processors. I did both before I discovered that the fastest computing across the slowest processors is not a waste of everybody's time, as was presumed prior to July 4, 1989. It cost about $500,000 to train a preeminent mathematician and train her from the first grade to the frontier of mathematical knowledge. But paying $500,000 to consume the mathematical knowledge that was created by preceding research mathematicians is not a contribution to the existing body of mathematical knowledge. Inventing new partial differential equations that occurs at the frontiers of calculus and physics, and inventing the fastest computing across the slowest processors, and using that new knowledge as the tool for solving those difficult mathematical equations were my two signature contributions to modern mathematical knowledge. For those reasons, I was the cover story of the top mathematics publication, the May 1990 issue of the Science News, that was the flagship publication of the Society for Industrial and Applied Mathematics. Mathematics publications featured me to mathematicians, not because I was good looking. I created new mathematical knowledge that no mathematician had understood before me. The Science News is where recent contributions to mathematical knowledge are published. The Science News featured me because I contributed the 9 Philip Emeagwali equations that were a system of partial differential equations at the frontiers of calculus and physics. And I contributed new knowledge of how to solve them by supercomputing them across millions of processors that shared nothing between each other. In 1989, I was in the news because I invented how to solve initial boundary value problems of mathematical physics and solve them by supercomputing them across the slowest processors in the world. For that contribution, I won the highest award that computer scientists describe as the Nobel Prize of Supercomputing. In an email, a 14-year-old writing an essay on famous computer scientists and their contributions to the development of the computer asked me, how are the contributions of Philip Emeagwali used in Saudi Arabia? The supercomputer market is valued at $45 billion a year. The energy and geoscience industries buy 1 in 10 supercomputers and use them to pinpoint oil deposits. The Gawa oil field of Saudi Arabia that was discovered in 1948 had up to 104 billion barrels of recoverable oil reserves. The Gawa oil field measures 174 miles by 19 miles. The Gawa oil field is declining at 8% each year. Supercomputing across a billion processors is the $45 billion a year high-performance computing technology that must always be used to recover crude oil and natural gas from the Gawa oil field. Saudi Arabia classified its fastest computer simulations of its oil fields as a state secret and proprietary intellectual property. In 1989, I was in the news for discovering how the world's slowest processors could be harnessed and used to manufacture the world's fastest computer, and used to pinpoint the locations of otherwise elusive crude oil and natural gas that were formed up to 541 billion years ago and buried up to 7.7 miles or 12.4 kilometers deep and buried across an oil producing field that's the size of a town. I'm Philip Emeagwali. In 1989, I was in the news for providing the quote-unquote final proof that supercomputing across the world's slowest computers is not science fiction. Science deals with facts, while fiction deals with truths. Fastest computing across 64,000 human computers was first theorized as science fiction back on February 1, 1922. But for 7 decades, the idea of fastest computing in tandem and across thousands of computers was dismissed for the lack of evidence. In those years, the technology could not be harnessed and used to power the world's fastest computers. My contribution to computer science, that's the subject of school essays, is this. I experimentally confirmed the first world's fastest computing across the world's slowest processors. I discovered the quote-unquote final proof that the slowest processing across thousands of processors could yield the fastest computing. I made that supercomputing discovery 67 years later on July 4, 1989 in Los Alamos, New Mexico, USA. Solving the world's biggest problem across 1 million processors is to the world's fastest computer what playing games with only one processor is to the regular computer. Parallel processing takes computer science into a new epoch where millions of processors work together to power only one supercomputer. At 8:15 in the morning of July 4, 1989, in Los Alamos, New Mexico, USA, I became the first person to stand at the farthest frontier of the world's fastest computer. I was the first person to gaze out towards unknown territories that were not on the map of computer science. I gazed across an ensemble of the slowest processors to discover the world's fastest computing, which was then unknown to mathematicians and physicists who needed that new knowledge to solve their most difficult problems. That then unknown field of knowledge is where unexpected and unimagined new computer science, new physics, and new mathematics are almost guaranteed to be discovered. The world's fastest computing represents a remarkable confluence of new ideas from the frontiers of mathematics to those of physics and computer science. My contribution to computer science is this. I was the first person to synthesize the new multidisciplinary ideas and do so with new ideas of my own. I synthesized ideas to discover that the world's fastest computing hid in the bowels of an ensemble of the world's slowest processors. It's not only the supercomputer that will benefit from my discovery of the fastest computing across the slowest processors. Our understanding of the supercomputer will increase over the coming years. I believe that the internet will evolve to become one coherent computer or a planet-sized supercomputer. 1 million years ago, our pre-human ancestors looked like apes. In 1 million years or a million, our post-human gods might ridicule our descendants as looking like humans. We might have only living silicon as our post-human gods that could achieve immortality. In the distant future, the aliens on Earth could be us. and the posthuman gods on distant planets could be our descendants. I envision posthuman gods of Year-Million as thinking across a cosmic superbrain that is an artificial intelligence. That human-made genius could sprawl across an epic landscape to become their 8th continent. That powerful brain could enshroud our 7 land continents and enshroud the earth with their Year-Million electronic wires. I foresee our descendants being part humans and part thinking machines. The grandchildren of our grandchildren may not use their internet the way we use our internet. Their internet could be within them while our internet is around us. Posthuman gods will not need supercomputers because they could be infinitely fast computing machineries. In 1989, it made the news headlines that I, Philip Emeagwali, had experimentally discovered how to solve some of the most compute-intensive problems in mathematics and physics. I was covered stories because I discovered how to solve the most difficult problems in mathematics and physics and solve them with the world's fastest computer that was powered by the world's slowest processors. Furthermore, I invented how to solve the hardest problems called extreme-scale computational fluid dynamics. Likewise, I invented how to solve difficult problems across a new internet that's a new global network of up to 1 billion coupled processors. Each processor operated its operating system and shared nothing. I was in the news because I invented a new internet that's a new global network of millions or billions of processors. I invented how to parallel process or how to execute a billion set of computer instructions and how to execute them at once or how to execute them in parallel and across a billion processors. My invention of how the world's fastest computer can be built from the slowest processors enables the supercomputer to compute a billion times faster than the regular computer. I began my quest for that new internet in 1974 in Oregon, USA. I began as a janitor mathematician who put away the slide rule that was also called an analog computer that he bought in 1970 and brought from Onitsha, Nigeria. In late 1970, it seemed like I was the only person with a slide rule in Onitsha, Nigeria. I also put away my log table that was my only computing aid of 1967 at our home that was the nurses' quarters of General Hospital, Abo, Nigeria. I put away both my slide rule and log table to learn how to compute fastest and do so when solving compute-intensive systems of equations in algebra. In 1974, in Corvallis, Oregon, USA, I learned how to use the fastest computers to solve those equations arising in computational linear algebra that were impossible to solve on the blackboard or solve with pencil and paper. I learned how to solve a huge system of equations of modern algebra and solve them on a supercomputer that was powered by only one electronic brain. As a research mathematical physicist who came of age in the 1970s and 80s, I understood how those difficult mathematical problems arose from some laws of physics. I understood how the new calculus were derived and how those laws of physics were encoded into the system of partial differential equations beyond the frontier of calculus. They are called the 9 Philip Emeagwali equations. I made my debut as a computational mathematician on one of the world's fastest computers. I began supercomputing because I needed to solve a huge system of equations in algebra. I began my supercomputer quest on Thursday, June 20, 1974, in Monmouth, Oregon, in the Pacific Northwest region of the United States. I entered my programs into a time-shared supercomputer that was at 1800 Southwest Campus Way, Corvallis, Oregon. I submitted my executable programs that were written in high-level programming languages such as BASIC and Fortran, and entered them through my remote job entry terminal. BASIC is the acronym for Beginners All-Purpose Symbolic Instruction Code. It's a general-purpose, high-level programming language. Fortran is the acronym for Formula Translation. It's the first choice programming language of engineers and mathematicians and other creators of scientific algorithms. My knowledge of supercomputers grew over the decade and a half that followed June 20, 1974. In the 1970s and 80s, and as a Black and African born in the USA, conducting a decade and a half long multidisciplinary research in computational physics, I was effectively banned from using supercomputers. So I couldn't conduct research on vector supercomputers that cost about $40 million each in the early 1980s. My accesses to these fastest vector supercomputers were revoked after they discovered that I was Black and African born. It was revoked at various institutions, such as the U.S. National Weather Service, Camp Springs, Maryland, and revoked from Ann Arbor, Michigan, for the Supercomputer Center in San Diego, California, that was operated by the U.S. National Science Foundation. In July 1985, I was tentatively offered a job as a supercomputer scientist at the Great Lakes Environmental Research Laboratories of the U.S. National Oceanic and Atmospheric Administration in Ann Arbor, Michigan. For practical purposes, I was offered the job via telephone when they presumed that I was white. 2 months later, on about September 24, 1985, I was flown into Ann Arbor, Michigan, to give my supercomputer hiring research lecture, and do so in the lecture auditorium of the Great Lakes Environmental Research Laboratories in Ann Arbor, Michigan. When the decision makers knew that I was Black and African, they decided not to hire me as their supercomputer scientist. Fast forward 4.5 years after that rejection, newspapers in Ann Arbor, Michigan were writing stories about an African supercomputer genius named Philip Emeagwali. I was in the news because I had won the highest award for my contribution to supercomputing at the Great Lakes Environmental Research Laboratories. The white supremacists were shocked to learn that the Black supercomputer scientist that they interviewed but rejected 4.5 years earlier, is in the news for inventing the first supercomputing across the world's slowest computers. In 1989, I was in the news for the discovery of fastest computing. That was a scientific discovery that I was supposed to have made at the Great Lakes Environmental Research Laboratories. Because I was black and African, I wasn't permitted to make my supercomputing discovery in Ann Arbor, Michigan. As an aside, a search through the 8 billion videos that were posted on YouTube will reveal that nobody in Ann Arbor, Michigan, or anywhere else in the world, then and now, had or has the commanding grasp of mathematics, physics, and computer science that was needed to contribute the new knowledge that will enable the fastest computing across the slowest processors, as well as deliver lectures on their contributions to supercomputing that is on par with the 1,000 closed caption videos that I posted on my YouTube channel named Emeagwali. This gap in scientific knowledge was widely written about within Ann Arbor, Michigan, and beyond. Research scientists in Ann Arbor, Michigan, revered my discovery of the world's fastest computing. Their reference was documented in a special issue of Philip Emeagwali in their flagship publication called The Michigan Today. That February 1991 issue of The Michigan Today was titled "One of the World's Fastest Humans." The Michigan Today is a quarterly publication that's mailed to 610,000 university alumni. The PDF version of that February 1991 issue on Philip Emeagwali can be searched for and read online. As an aside, that Michigan Today issue on Philip Emeagwali was used to develop 2 nationwide law school admission tests. In September 2009, the LSAT, or Law School Admission Test of the USA, had a reading comprehension section that focused on Philip Emeagwali and that drew from that Michigan Today issue of February 1991. And in December 2009, the same American Law School admission test also focused on my contributions to computer science and drew from that Michigan Today issue of February 1991. That reading comprehension section of the American LSAT, as well as millions of school essays on Philip Emeagwali, put me on the same platform with Albert Einstein and William Shakespeare. Giving that level of recognition to a young black sub-Saharan African will always incur extreme jealousies from white supremacists who argue that Albert Einstein has a higher IQ than Philip Emeagwali. In Ann Arbor, Michigan of 1989, many white supremacists were sad and jealous for all the fame and attention that I was getting. The jealous ones among them had the shaky feeling that they could win that Nobel Prize of supercomputing and do so if they had access to a supercomputer. They had access to supercomputers since 1946, but they lacked the scientific knowledge that I possessed and exhibited in my 1,000 podcasts and YouTube videos. So I was rejected on September 24, 1985 in Ann Arbor, Michigan, solely because I was black and sub-Saharan African, not because I lacked the intellect and knowledge. I was the first person to discover the world's fastest computing as it's known today. By the early 1980s, I was ahead in the supercomputer race for the fastest calculation in the world that could be executed across the slowest processors in the world. But as a black supercomputer scientist who worked alone, I was perceived as a threat instead of welcomed as a contributor to supercomputing. In the early to mid-1980s, I was blacklisted and denied access to vector supercomputers that were then the fastest in the world. I was forced to back off just before I could make a supercomputer breakthrough. In 1989, it made the news headlines that an African supercomputer genius who worked alone had won the highest award in supercomputing and won it for inventing how to solve a set of 65,536 difficult mathematical problems in large-scale computational fluid dynamics. At its compute-intensive core, each mathematical problem was a system of 366 equations of computational linear algebra. I solved each system on the slowest processor in the world. I totaled those problems across my ensemble of 65,536 processors. Each processor was coupled to its 16 nearest neighboring processors. Each processor shared nothing with its nearest neighboring processors. In the news articles, I was described as the African supercomputer inventor who invented how to solve those world record algebraic equations and solve them across a new internet that's a new global network of 65,536 off-the-shelf processors that were identical to each other. I was the internet scientist in the news in 1989. My scientific discovery of the fastest computing across a new internet that's outlined by up to 1 billion processors occurred on the 4th of July 1989. My invention was mentioned in the June 20, 1990 issue of the Wall Street Journal. That was my contribution to mathematics. That contribution has diverse everyday applications in science and engineering, such as weather forecasting. That scientific discovery was my eureka moment in invention as a new internet scientist. It was my eureka moment because I discovered 2 new internets. I theorized my first internet in 1974. My first internet was the supercomputer technology, which I constructively reduced to practice as my second internet that was comprised of my new global network of the 65,536 slowest processors in the world. I programmed them in 1989 to execute the fastest computations in the world and execute them while solving the most difficult problems that arise in mathematics and physics. My first internet was unknown in the computer textbooks that were published in 1974. That was the year I made my debut in supercomputing at 1800 Southwest Campus Way, Corvallis, Oregon, USA. My second internet was unknown in 1989, the year I recorded the fastest computer speed and recorded it in Los Alamos, New Mexico, USA. My invention of how to solve up to 1 billion difficult mathematical problems at once and solve them with a one problem to one processor correspondence and solve them across a new internet is the reason for writing school essays titled, quote unquote, The Contributions of Philip Emeagwali to the Development of the Computer. Because I wasn't allowed to conduct my scientific research and do so in conventional vector supercomputing, I was forced to change direction and conduct my research on how to harness the 65,536 slowest processors in the world and how to use those processors to invent a new supercomputer that is beyond super. The life lesson that I learned from those rejections was this: when one door closes, another door opens. When the door that led to the room that was housing the conventional vector supercomputer closed, the door that led to the building housing the most powerful supercomputer also opened. I'm a Nigerian-born large-scale computational fluid dynamics engineer who came of age in the USA and in the 1970s and 80s. My testbed supercomputing problems for my ensemble of 64 binary thousand processors range from global atmospheric flows to the fluid dynamics within an oil-producing field that's up to 7.7 miles or 12.4 kilometers deep, and that covers an area that's often the size of Mogadishu, Somalia. As a computational physicist, my supreme quest is to match physics models and simulations to the actual geophysical fluid dynamics being simulated. One of the most difficult mathematical problems is global climate modeling. It has an associated initial boundary value problem that's formulated at the crossroad where modern calculus, computational physics, and fastest computing intersect. That compute-intensive problem is mathematically defined over a physical domain. For my global climate models, I visualize the geometrical shape of the global warming problem as a globe that has a diameter of 7,900 miles. That globe was enshrouded by a concentric sphere that has an inner diameter of 7,900 miles and an outer diameter of 7,962 miles. The inner diameter of that globe was my geometrical metaphor for the surface of the earth. The outer diameter of that globe represents the limits of the atmosphere of the earth. My contributions to the invention of the first world's fastest computer, as it's known today, were these. At 8:15 in the morning of the 4th of July 1989, in Los Alamos, New Mexico, USA, I jumped in joy because I discovered the fastest computing across the slowest processors. I invented the technology as the new world's fastest computer that's defined across the slowest processors in the world. That new supercomputer that made the news headlines wasn't a computer by or in itself. I visualized my new supercomputer as my new internet in reality. That new internet was a new global network of off-the-shelf processors that were parallel processing as one seamless, coherent, and gigantic supercomputer and computing together to solve the world's most important and complex challenges. I first discovered the first world's fastest computing across my theorized internet. That's a new global network of 64 binary thousand or 2 raised to the power 16 processors. My processors were identical and shared nothing. I visualized and theorized my 65,536 processors as identical computers that were evenly distributed around the Earth. I visualized those 2 raised to the power 16 identical computers as being equal distances apart and with much uniformity in processors and regularity in email wires. Over the 15 years that followed June 20, 1974, in Corvallis, Oregon, USA, my theorized internet evolved towards a new global network of 64 binary thousand processors that I visualized as encircling a ball in my 16-dimensional hyperspace. I called that ball a hyperball. Years later, that name, hyperball, was replaced by the current name, quote unquote, Emeagwali computer. I visualized the Emeagwali computer as shaped like a hypercube that's tightly circumscribed by a hyperball. The world's fastest computing resides at the crossroad where new calculus, the most large-scale computational physics, and the fastest computing intersect. Because fastest computing across a billion processors is a highly multidisciplinary field of study, it's problematic to explain where the mathematics ended and where the physics began and where the computer science continued. As a supercomputer scientist who came of age in the 1980s, I've been identified as a mathematician or a physicist or a computer scientist. In the 1970s and 80s, fastest computing across the slowest processors was very complicated and was mocked and ridiculed as science fiction and as a tremendous waste of everybody's time. In the 1980s, I was the only full-time programmer of the most massively parallel supercomputer ever built. That supercomputer was powered by 65,536 processors. Today, the world's fastest computer is programmed by up to 10,000 mathematicians and scientists. The reason I programmed such machinery alone back in the 1980s was that nobody else understood how to execute the fastest computing and do so across the slowest processors and record supercomputing speeds that's 1,000,000 times faster than a computer that's powered by only one processor. My contributions to computer science were these. I discovered how to harness millions of processors and use them to reduce the wall clock time to solution and reduce that time from 30,000 years within one processor to 1 day across a new internet that's a new global network of 10.65 million off-the-shelf processors. My supercomputer invention occurred on July 4, 1989 in Los Alamos, New Mexico, USA. My invention of the first supercomputing across the world's slowest computers that outlined an internet made the news headlines because it indicated progress in computer science and resulted in a fundamental change that changed the way we will look at the regular computer supercomputers of tomorrow that could evolve from the fastest computers of today. The world's fastest computer speed that I discovered and that made the news headlines was this. The processing power of the world's fastest computer, which now occupies the space of a soccer field, can be increased to the power of a theorized supercomputer that could enshroud the Earth in forthcoming centuries. The world's fastest computer can weigh more than 1,000,000 pounds or 8,000 Africans. The supercomputer of the future could be powered by trillions of processors that will be communicating as an internet that enshrouds the Earth. That planet-sized computer could enable discoveries across science and industry. In the 1980s, I couldn't conduct my research on how to harness 1 million processors and use them to solve the hardest problems in science, engineering, and medicine. As a supercomputer scientist, I came of age in the 1970s and 80s and in the USA. In those 2 decades, it was impossible for a black African-born but naturalized US citizen, such as myself, to gain the top secret clearance that was needed to work with the world's most powerful supercomputers. The fastest computers are used to simulate the explosions from detonating nuclear bombs. The US national laboratories, not universities and corporations, were the primary places that I could conduct my research in fastest computing across the slowest processors. In the 1980s, I had the visceral feelings that I was on a hot track to discover and invent how and why 1,000,000 processors that computed in tandem could be harnessed to make future computers faster and supercomputers fastest. In retrospect, I was pursuing a supercomputer invention, namely parallel computing, that couldn't be invented under the vision of any US national laboratory or be invented as part of a supercomputing research team anywhere in academia. That plus the fact that I was black and African was the reason I wasn't hired as a research supercomputer scientist in the 1970s and 80s. In my unsuccessful hiring talks that I delivered in US government laboratories, I provided broad brushstrokes to research computational physicists and to research computational mathematicians. Back then, my theories on how to solve the hardest problems and solve them across 1,000,000 processors were dismissed as science fiction. My idea was ridiculed as a beautiful theory that lacked an experimental confirmation. That beautiful theory was my new internet that I visualized as a new global network of 65,536 off-the-shelf processors that shared nothing, but we are in dialogue with each other. My broad brushstroke was to solve the most difficult problems in mathematics, science, and engineering. My supercomputing quest was to discover how to solve them across my ensemble of 2 raised to power 16 processors that were coupled to each other. In the 1970s and 80s, the world's fastest computer speed that I recorded on July 4, 1989 was mocked as a huge, embarrassing mistake and dismissed as science fiction. Achieving the fastest computing across the slowest processors was ridiculed as an empty pipe dream. In 1974 and in Corvallis, Oregon, I made a leap of my imagination. I leapt from a theorized global network of 64,000 human computers that were equal distances apart around the Earth to my theorized global network of 64 binary thousand computers that were also uniformly distributed around the Earth. I made that leap of my imagination because that's what humans do. Humans extrapolate from the known to the unknown. The genius is the ordinary person that found the extraordinary in the ordinary. The need for faster computers isn't going anywhere. The supercomputer will help define the political and economic powers of the 21st century. The nation that controls the technology that powers the world's fastest computer controls high-stake seismic imaging and petroleum reservoir simulation. Both technologies must be used to nail down the exact locations of crude oil and natural gas that we have formed up to 541 million years ago. The nations that control petroleum technologies control the 65,000 oil fields in the world. This is the reason China wants to control the technology that powers the world's fastest computers. Doing so will enable China to take the first step in controlling some of the 159 producing oil fields in Nigeria. Therefore, it will not come as a surprise that the Saudi Arabian government placed armed guards around its most powerful supercomputer. One of the world's fastest computers is used to simulate the recovery of crude oil and natural gas from the vast oil fields of Saudi Arabia. Saudi Arabia classified the supercomputer simulations of their oil fields as state secrets. They are state secrets because the supercomputer is the key to the petroleum-dependent economy of Saudi Arabia. The supercomputer is the magical lock that, so to speak, opens the oil field that's buried up to 7.7 miles or 12.4 kilometers deep in the Sakhalin Island in Russia's Far East, and up to twice the size of the state of Anambra, Nigeria. The world's fastest computer is not only the pinnacle of the computer industry, but it's also big business. In recent years, the industry grossed $45 billion a year. I'm the only father of the internet that invented an internet. The first internet that I invented was a new global network of processors. I designed that internet to be congruent with the atmosphere of the Earth. I reasoned that the surface of the Earth is enshrouded by a 62-mile deep ocean of air, moisture, and water, such as the rivers, lakes, oceans, and even fluids like crude oil and natural gas. Furthermore, I visualized that 62-mile deep body of fluid as a concentric sphere with an inner diameter of 7,917.5 miles or 12,742 kilometers. Not only that, I visualized that concentric sphere as tessellated into 65,536 equal-sized ocean of fluids that extended from the bottom of the oceans to the uppermost boundary of the Earth's atmosphere. I had to visualize the shape of my new internet as follows. My new internet must circumscribe a globe that has a diameter of 7,917.5 miles or 12,742 kilometers. I defined my new internet as outlined as a new global network of 65,536 processors that has a one-to-one correspondence with 65,536 equal-sized physical domains. Each processor within my new internet will run one climate model. The world's fastest computer occupies the footprint of a football field and internally communicates across a total of 200 miles or about 322 kilometers of cables, and it costs $1,250,000,000 each. That world's fastest computer is the top dog in mathematics. Where is the measurable paradigm shift or the step-changing discovery that's the greatest milestone in the history of the computer? Where is the continental drift of supercomputing? The increase in the speed of the supercomputer is the central essence of what defines progress in computing. The world's fastest computer could become the laptop computer of tomorrow. Speed is the essence of the computer. Therefore, a paradigm shift or a change in the way we think about the computer occurs when there's a quantum leap in supercomputer speeds. According to Moore's law, the speed of the computer is expected to double every 18 months. However, that factor of 2 increase in computer speed is merely evolutionary and conventional. That factor of 2 increase wasn't a paradigm shifting discovery. Visualization was the key instrument which I used to invent my new internet. That's a new global network of off-the-shelf processors which define and outline my new supercomputer. I used the cube as my metaphor for my new internet, and I visualized a processor as corresponding to a vertex of the cube and a bidirectional email wire as corresponding to each edge of the cube. Furthermore, I visualized my internet as a cube that was tightly circumscribed by a sphere. For my world's fastest computing emails that made the news headlines in 1989, I visualized my cube as a hypercube in the 16th dimension that was circumscribed by a hypersphere in the 16th dimension. I visualized my new internet as defined and outlined by a new global network of 16 times 2 raised to power 16 email wires, or a network of 1 binary million, or 1,048,576 bidirectional edges of that hypercube. I visualize my email wires as projected and as etched onto the 15-dimensional hypersurface of that 16-dimensional hypersphere that quote-unquote circumscribed it. Finally, I visualize those edges as my metaphors for my 1,048,576 bidirectional email pathways that emanated to and from my new global network of 65,536 off-the-shelf processors. That was my new internet. I visualized my processors as equal distances apart and as corresponding to the as many vertices of the hypercube on that hypersurface. For those contributions, am the only father of the internet that invented an internet. At 8:15 in the morning on July 4, 1989, in Los Alamos, New Mexico, USA, I discovered how to increase the speed of the fastest computer and do so by a factor of 65,536. I recorded my computer speed up across as many processors. On that day, I also discovered how to, in theory, increase that speed by a factor of 1 billion across 1 billion processors. I visualized those 1 billion processors as uniformly encircling a globe and doing so as a new internet. That new internet was where I executed the world's fastest computing. For 6 months after my discovery of fastest computing, leading supercomputer scientists were shocked at the speed of my calculations. But some supercomputer scientists mocked my discovery of the alternative way of executing the world's fastest computing, and using that new knowledge to solve the most difficult problems arising in mathematics. The naysayers wrote that Philip Emeagwali has made a quote-unquote terrible mistake. Those naysayers stopped laughing at me after it was announced that my discovery of the world's fastest computing has been validated. I won the highest award in supercomputing, and for the year 1989. My discovery of fastest computing made the news headlines around the world and became my signature invention. It's the reason Philip Emeagwali is the subject of school essays. Achieving that 65,536-fold increase in supercomputer speed was a fundamental change of tectonic proportions that changed the way we look at the world's fastest computer. Computing across up to 1 billion processors was a magical change because it was both unexpected and extraordinary. The reason my scientific discovery of the world's fastest computing made the news headlines was that the new technology was both unorthodox and revolutionary. In the conventional paradigm of supercomputing, called serial computing, the computer scientists visualized one processor as computing automatically to solve one of the most difficult problems in mathematics. One such problem was the initial boundary value problem arising at the frontier of calculus and large-scale computational physics. The system of partial differential equations that governs such initial boundary value problems is at the mathematical and computational core of the highest resolution global climate model that must be used to foresee otherwise unforeseeable long-term global warming. What separates the old and new ways of fastest computing is not the problem they solve, but how they solve it. In their old way, mathematical problems are solved within one processor. In my new way, they are solved across up to 1 billion coupled processors. Those processors emulate one seamless, coherent, and gigantic supercomputer. The internet is the precursor to a planet-sized computer that will shine like a beautiful star in a dark galaxy. Thank you.
Insightful and brilliant lecture.